This is Dave Hicks, and today we're going to talk about mass spectroscopy. You know, lately I've been recording this series on how we analyze hydrocarbons, and carbon's such an amazing atom. It can bond together in so many different ways to create all the myriad of complex molecules that are around us. And one of the questions that comes up is, how do we know what we know? How do we know all of these different shapes and when they show us a picture of a molecule, how do we know that that really looks like that? How do we know the bonds are this way, or whether it's an ester or whether it's a carboxylic acid? How do we know? And so this segment of videos that I've been doing is kind of going through 4 different types of analyzing techniques. And each one of them gives us a little clue about the bonding and the way that these molecules are actually put together. And so today is going to be another one of those clues with mass spectroscopy. So mass spectroscopy, or mass spec as they sometimes call it, is something that it starts out with a machine that takes the molecules that are put inside of there and it ionizes them. It gives them a charge. And during this time when it is ionizing it, it's giving it a charge, giving it positive charges. It's knocking electrons out of the molecule. It also causes the molecule itself to break up into different pieces, or what we call fragment. And some of these pieces that come out of there, they all have different masses. So some of these pieces that come out of there, some of these different fragments, are commonly known. And we can figure out what their masses are using a little physics. And we tend to see them over and over. So they're commonly known fragments. If you're taking IB, there's a table that contains some of the common fragments that come from a mass spec. And we're going to look at those in a moment. The big thing, though, is about the most massive fragment, the largest fragment itself. And that fragment is the molar mass, right? And so the entire molecule, put all together, that piece is the molar, the entire molecule, and you will see one peak, the heaviest peak, is going to be the molar mass of that particle itself. I think maybe the most useful piece of information in a mass spec. So when you do a mass spec and you run a mass spec on a particular molecule, you get what's known as a spectra. And here's an example of a spectra right here. Now down here on the x-axis, down here, these are actually the masses of things that we're talking about, okay? So you can see here the heaviest mass piece right here is the molar mass of our molecule. So this is the cocaine molecule up here. I chose this one not because I have a fetish with cocaine, but because it's something that I used that was part of my index of hydrogen deficiency as well. So you will get to see different ways of seeing how this molecule looks. Plus, it's really kind of a cool looking molecule, right? It's got that got those little ring structures. It's got some esters going on in there. It's just kind of a neat looking molecule. Anyways, in looking at this and in analyzing it, we can see that it has a molar mass, and that's right there, of 303. So this is one peak that you can always kind of count on right here. The largest peak of it is going to be the molar mass, huh? So I'm just jotting that in there if you're taking notes. My pen's giving me a little trouble, but that'll be okay, huh? All right. So anyways, the other big thing that I can say is that the y-axis here has to do with a relative intensity. So what we mean by that is as these particles slam into the detector inside of the mass spectrometer, then they're going to create an electrical signal. And the more pieces that slam into that detector, the greater the signal is going to be. And so we get different sized peaks here, right? Some of them are small, like this 198. Some of them are really big, like this one at 82. It has to do with the relative amounts of pieces that break off of this molecule that it fragments into. And we generally try to look at the really big peaks. So the ones that are generally big. However, a trained person who can look at these, and they are very specialized people, organic chemists who look at these and can interpret these, they can make sense out of a lot of the peaks. And you have isotopes that play an effect with this. You have recombining of particles after it's been fragmented, that plays a part in this. There's a bunch of math that goes along with how many of these little fragments are going to show up. And so it is very complicated. But for us, untrained people, we tend to just focus on the ones that are really big and maybe try to make some sense out of those. Here's maybe my biggest, most important thing for you as a novice person. Don't try to interpret every peak that's on here. And if you do that, you'll drive yourself insane and you'll never be able to figure this out. Remember, each of these 4 different techniques provides us with some clues. Not any one of them is definitive. We can't look at any one of these analysis techniques and say, oh, well, I can tell exactly what this molecule is. We use little clues from each one to try to come up with what is this piece. What is this molecule shaped like? How is all of these atoms bonded together? Okay? Let's talk about this breaking up a little bit, because this is important in understanding that you don't have to analyze every piece. So first of all, inside the mass spectrometer, where this takes place, where things are being ionized right here, you get all of these fragments at once. So it's not like we're just breaking off one little piece at a time and weighing it. It's like we just blow this molecule up into all kinds of myriads of different pieces. And they all come flying down this tube at the same time. Now, hopefully you've talked about mass spectroscopy before, and you kind of understand that the heavier particles are going to try to go straight, aren't they? And if they do that, let me try to draw a blow up of this area here, trying to draw the tube as it bends, So here's the tube bending. And as a particle comes down here, if it's too heavy, then the magnetic field just doesn't cause it to bend enough, and it will hit the side of the tube that it's going down. Some particles are too light, and the magnetic field will cause it to bend too much, and then they will run into the other side of the tube. And some particles will have just the right mass, and they will go down and they'll be able to hit the detector, right? We can vary the amount of magnetic field that we have here, and that causes more of the particles to either bend either more or less. So they would run through different magnetic field strengths here, and that would make it so that more of the different particles would collide with the detector. So if they want to get a reading on this one, of course, they would have to increase the strength of it, right? If they want to get a reading on this one, they would have to decrease the strength of the magnetic field so that it can come and bend the proper amount and hit the detector. So that's how they do it. And then they just record, how many pieces are hitting it in this relative way because of the electrical charge that's being transmitted there with some electronics. Now, here's an important little tidbit. Not every piece has a charge. Now, this is, I think, an important part of understanding mass spectroscopy, okay? And as we talk a little bit more, that's why I'm going to take just a moment to explain this. So let's say we have a particle. I have A and B that are together, okay? And inside this area here, in the ionizing section of this, we're going to give this a charge. It'll be a positive charge, okay? So now this particle has a charge. Now, if this particle breaks up as well as gaining its charge, okay, there are two possibilities of what can happen if this breaks up. Let's say it's going to break up into piece A and it's going to break up into piece B. Now, it can be that B, let's say particle B will get the charge and particle A will not have a charge. Or another possibility is that particle A is going to get the charge, right? And particle B will not get the charge. Because if this breaks up, charge has to be conserved. So that means we aren't going to go from +1 charge and having both particles charged and having a +2 now. That would be against our rules of matter. So only one piece is going to get the charge as it breaks apart. Now, which piece gets the charge? That is the art of understanding mass spectroscopy. You see, specific pieces tend to get the charge. And that's what I meant back in the previous slide where I said, we know certain fragments tend to get that charge. And these are the fragments that hit the detector. If the piece doesn't have a charge, it will not be affected by this magnetic field. And then that particle, an uncharged particle, is just going to go straight. And it's going to run into the side of the tube here and be vacuumed out of the system. So the only particles that are going to turn or curve in this tube are going to be the charged particles. And not every piece has a charge. Certain pieces tend to get the charge just based on the way things are bonded together. So there are certain peaks that are going to show up in mass spectroscopy, and those are the ones that we kind of let our eyes take a look at. Those are the peaks that are going to be those tall peaks. So we try to make a little sense out of the tall peaks, and the other peaks, can't always figure all of them out. And we recognize that not every part of this molecule is going to show up in a spectra. All right? So, with that said, I know that's making things sound really fuzzy, isn't it? Let's see how we use this, and I'll take 2, 3, 4 molecules here, and we'll just kind of talk about this a little bit. So this is the mass spectra of ethanol. So let me write out what ethanol is here. So I've got a carbon, and we got 3 hydrogens on here, right? And then I have another carbon and a couple of hydrogens and an oxygen and a hydrogen. There we go. So this is going to break up into pieces. Now, the first thing I'm going to do is go way down here, and I do this every time. It's the very first peak that I look at, and I look at that peak right there. So this is 40, and let's see how it's broken up. 1, 2, 3, 4, 5 to get to 10. So each of these lines must be 2, right? So that's 42, 44, 46. So this peak right here is at 46. What did I tell you that was? That's right. That's the molar mass of ethanol. And if you add it up, I got what? 24 and 16 and 6. So you put all that together, and that's 46. So that's the mass of our ethanol molecule right there. So that's one critical peak that you can always count on every time. Next thing is I do have this one really big peak right here, right? It's the majority peak. And so I'm kind of interested in whichever one is the biggest. My eyes kind of go to that one. I'm not going to try to make sense out of every single line that's on this spectra. I'm going to go to the big major ones, and I'm going to try to make a little sense out of them, okay? So I'm looking for a piece that could be around 31, huh? So this peak is around 31. And I can see down here, here's 32, there's 30, so it's a piece around 31. So I'm going to look at different ways I could break this molecule up into pieces. So let's consider breaking the molecule up right here. Let's say that that bond right there broke up. And so what would we have? If that broke up, I would have two pieces. I would have this CH3 piece, right? And then I would have this other piece that would be a CH2 and an OH. Yes? So how much does this piece weigh? See, if I broke that up, if this molecule broke right here in the middle and had those two pieces, what would I have? This piece here would weigh 15, right? And this piece over here then, so 15 minus 46, oh, how did I get that this was 15? The carbon is 12 and 3 hydrogens, right? So that would be a mass of 15. And over here, the mass of this then would be the remainder of it, which 15 subtracted from 46 would be 31. Ooh, look at there. That's a piece right here, isn't it? 31. Now, is there a piece at 15? Yes, there is, but it's kind of small. Right there it is, at 15. So this piece is a little small for us. And again, why? Because when this breaks up, one of these pieces is going to take the charge. So I would imagine the majority of the time when this breaks up, this piece here takes the charge with it, and the methyl piece over here tends not to take the charge with it most of the time. And again, this is a bit of a random process. It's not like every time it's going to take that particular piece. Now, can I make sense out of any of these others over here? Well, there is another piece here that I look at that's part of the table on, especially if you're an IB student, and that's this one here at 29. So 29 is another piece that shows up quite often. And 29 can be made up from a combination of this right here, the carbon, an oxygen, and a hydrogen. Now, do I know if it's this hydrogen or that hydrogen or that hydrogen? I don't know. But I do know that if you add up 12 and 16 and 1, that this piece right here has a mass of 29. Does it give me any really good information? No. No, other than I know that there might be a carbon, an oxygen, and a hydrogen that's bonded together somewhere out there. So, and you know, again, it could be this carbon, oxygen, and hydrogen. I have no clue which one it is, but I know that there is a piece out there that's a carbon, oxygen, and hydrogen, and it tends to break off a lot of time and stay together. All right. So that was a little picture of ethanol, and hopefully what you took away from that one is that it breaks up into multiple pieces, and we try to look at the mass of those pieces. So, you know, we're trying to figure out what this is. We have some ideas as to what this molecule could be, and then we sit down and we think about how it could break up, and we consider what those masses would be, and then we take a look at our spectra and we say, yeah, I do see that mass sitting there like that. that could possibly be an alcohol. Are there other possibilities of this formula? Are there other isomers of this formula? The answer is yes. Dimethyl ether has exactly the same chemical formula as ethanol does. And as you can see, when I switch to this, this has a different mass spectra to it, doesn't it? It looks different. Here, I'll flip back just so you can see. There's the ethanol spectra, and here's the dimethyl ether spectra. They look very much different from each other. And so one thing that I can see that is missing, let's draw out first the dimethyl ether. I'm getting ahead of myself here. So it's a CH3, okay? And then there's an O, this is the ether in the middle, right? And then that's bonded to another carbon here, and 3 more hydrogens. So it's the same chemical formula, but it's put together differently. What's most notably missing from this that was part of the other one was the alcohol, is that there's no OH group, is there? Now, that's where I'm getting back to this mass spectra here. We can see over here, here's our biggest, here's our most massive peak, right? And that's these look like they're ones. So that's 41, 2, 3, 4, 5, and 6. So you can see there's its mass again at 46. That's the molar mass. But now I have this really big peak at 45, right? You know, and again, you can try and interpret what this really big peak here is at 45 if you want. And what would that be? Well, I could imagine that it may be if this broke right here, yes, and it lost just 1 hydrogen atom, then the remainder of this peak, the remainder of that molecule would be 45. Now, does that help me out too much? No, because the alcohol could have done that, right, and lost a hydrogen, and then it would have had a mass of 45. So that didn't help me out too much. One thing that I can see that is noticeably missing from this one is this does not have that big peak at 31, does it? So here's 31 like we saw last time. And remember, the 31 was made from that peak where it was a carbon and 2 hydrogens and an oxygen and another hydrogen, wasn't it? So could this one make a piece like that where I have 3 hydrogens and an oxygen together? And the answer is absolutely it could. So if it breaks up into these 2 pieces right here, then I would have this piece with 15 and I would have this piece over here with 31. But you'll notice that, you know, that is not an overly prevalent peak, is it? And so that is one way that I can use as a clue to distinguish between these 2 different molecules. I can learn from experience and learn and say, hey, when it's an alcohol, I tend to get this big peak at 31. When it's not an alcohol, I tend not to get that big piece. Could it make a fragment of 31? Yes, it could, but obviously, this is not the piece that gets the charge the most of the time, is it? Remember, when they break up, one of the pieces takes the charge. If you were to ask me, it kind of looks like the methyl piece might take the charge when it's breaking up from a dimethyl ether. So this is the piece over here that probably gets the positive charge. And look at here at 15, right? Here's our peak at 15, and you'll see it's much more prevalent in this spectra than if we go back and take a look in this spectra. Look at it, it's really small over here compared, it's much bigger with the dimethyl ether. So again, are you as an untrained person going to be able to make sense out of every little piece in this spectra that you get? The answer is no. we use each of the little pieces to try to make some sense out of it. We use some historical information, like I recognize this as an alcohol. This is the way alcohols tend to break apart. And this is the way ethers tend to break apart. So it's a lot of experience in a lot of different ways, but we're just kind of looking at another one of those pieces. All right, let's look at another one that's a common molecule. How about ethanoic acid, right? So I'm going to draw out ethanoic acid here. I got a CH3 and another hydrogen, another hydrogen. We got that double bonded oxygen, right? An O and an H. So here's my ethanoic acid. I can come down here. I see this really big piece at 60. Trying to make a 60 there. There we go. I see this really big piece at 60, and I can see, hey, that's the molar mass of it, right? 24, 32, and 4. So we put all those together, we're going to get 60. So again, we're going to kind of look for big pieces that have broken up and try to make some sense out of them. Here's a piece that we've seen a couple of times now, except it's not super big, but it's, you know, bigger than the normal, and that's this one right here at 15, right? So we've seen that 15 kind of represents that CH3 group, doesn't it? And then I'm looking over here, I see, all right, there is a CH3 group in ethanoic acid right here. So if it broke right there at that bond, then we would have a 15 CH3 group that would come out of this, yes? So if I subtract 15 from 60, that's going to leave me with 45. Do I see a peak at 45? Well, here's 41, 2, 3, 4, and 5. Yeah, there's a pretty big peak right here at 45, right? And so this peak at 45 could be, you know, that piece right there. If that breaks off, then this piece is going to have a mass of 45. And this piece over here, this other piece, the methyl group, is going to have a piece of 15. So I can see those two peaks that are part of this. Again, we're not going to try and interpret every one of them, but I can see when a carboxylic acid, when a carboxyl group is present, that a lot of times I will get this peak around 45 or so. Again, can you say every time you see 45 that it's going to? No, you can't really say that. But if your inkling is, or if you're looking at different possibilities for what this molecule can be, and one of the possibilities is a carboxylic acid, then you would look at this, and if you'd had a piece at 45, you'd say, maybe this is a carboxylic acid, right? There are other pieces too, like this really super big ones at 43. What's that? Can I make sense out of that? Well, let's see. If I have 43, here's 15. And then the C and the O here, if I put these two together, the C and the O is 12 and 16. So this piece here is 28, right? So 15 plus 28 then would be 30, 43. What do you know? That piece that's 43 would just be this right here. So if instead of breaking at this carbon, let's say it's breaking here and it's breaking the OH off of the carboxylic acid, then my leftover fragment would be 43. So again, you see in my technique or my approach for this is I'm taking a look at these big peaks. I'm taking a look at the molecules and the possibilities of these molecules, and I'm saying to myself, are these pieces present? And do they have the masses that I'm looking for? And that's how we work with mass spectra, is we just try to sort them out based upon the structures and the possibilities of structures and look at the peaks and see if they match up to it. What you can't do is this. All right, so I have one more spectra, and I just want to try to emphasize something, all right? So here's another spectra. I'm not going to tell you what it is. You can't just sit down and look at this spectra and try to figure out which every one of these pieces are. Now, I can look at some things and say, all right, well, here's my 15 over here, right? And I know that a lot of times 15 goes along with this CH3 group. I can tell that. But look, here's a 29 and a 31. They're really small. I'm not so sure what that is. I can see that it has a molar mass of 74. So I know that's what its molar mass is. And over here, I do see a particle, a really big major particle is around 43. Have I seen this particle around 43 before? Has this been important? You bet I have. It was back here with the ethanoic acid, right? We had a particle that was 43, where I had my 15 and my 28 go together and it made 43. Does that mean that's what this particle is? Maybe. Does that mean this is another carboxylic acid? No, probably doesn't mean that it's that. Let's take a look at this. When we had our carboxylic acid, we had a piece at 45, didn't we? And we'll notice here at 45, though I have a little tiny peak there, there's not much of a peak at all at 45. So again, see, you can't always go and try to figure out what every single peak is. You just, the best way to do this is you can't just take a spectrum and figure out what the molecule is. The best way to work with mass spectra is to have possibilities of the molecule and draw those possibilities out. And then take a look at your spectra and see if you can make sense of the different masses in your spectra and relate those to the different possibilities of molecules. And again, just to emphasize this one more time, not any one of these techniques gives us the answer. You have to take clues from each of the techniques that we have, the chemical techniques, the spectra techniques. You have to put them all together in order to try and figure out what the molecule structure is. And that's what's kind of fascinating about it. It's great brain food for you to try to figure some of these things out. And so anyways, that concludes today. I hope you're having fun with your chemistry. This is really neat stuff. And I'll see you again next time.